So I can do the integration there. So I will get two cos terms after putting the limits 0 to L. So I will get two cos terms, and these cos A minus cos B I can convert into product terms, which is sine into sine. So after doing some mathematical computation here, n is actually n0. N0 is the initial carrier density into L divided by saturation velocity into 1 plus twice m saturation velocity of the electron into omega L. Omega here is the frequency, L is the length of the device, and sine omega L 2 VSC sine omega t minus L by 2 SC. So if I want to calculate the current in the external circuit, the current in the external circuit will be number of electrons into E saturation velocity divided by L. So this I value, after putting omega is equal to 2 pi f, I get something like this. So this is the current which is produced in the external circuit. So the current which is generated in the external circuit is N0 into E 1 plus m sine pi ftr. Tr is the transit time, sine into 2 pi f into t minus t transit by 2. So this is the current which is generated in the external circuit. Now you see there are two things here. This modulation is modified. Earlier it was m sine omega t or m 2 pi ft. Now it has become m sine pi ftr. Something like this sine f pi ftr over pi ftr is sinc function, right? And the other thing which you notice here is that there is a delay which is given by this term. So the resultant current which is generated follows the modulation index is modified from say m to m dash, and it has become m sine pi ftr divided by pi ftr. And the second thing, it has introduced some delay. This term basically is the delay part, and this is your modified modulation index. And if I plot this is the modulation index m dash rather. It will be sinc function, and basically this is say f, and this f is equal to 1 by tr. So you can take the value of tr as some 0.5 nanosecond, and accordingly you can calculate the value of f. So that actually becomes the response time of the device. So it basically depends on the transit time, and the contribution to this transit time is both coming from drift as well as diffusion. So you have to make your device in such a way that diffusion component is much less, and the whole electron hole pairs are generated inside the I region, so that your transit time is as low as possible and you get good response speed of the device. So this is what I had explained, that modulation index is modified. M dash has become m sine pi ftr or m sinc x of this form. So now, just to put the things in perspective, the total response time of the photodiode depends on the transit time of the carrier in the depletion region. This we have seen, this is a function of TR, transit time. it also is a function of diffusion time of photon carrier generated outside the depletion region. Remember our structure P, N, I. So there is a diffusion component here, there is a diffusion component here, there is a drift component here. So this response time will depend on this diffusion time of the photocarrier generated, which are generated outside the depletion region, which is my I region here. The third component is, you have when you use this device, you have some external component RL, right? And then there'll be some capacitance of the device, some call it junction capacitance. And if you have some equalizer, then it'll have some R and C component. So basically it also depends on because ultimately I have to see the response time of the whole device, not just the photodiode. It is a receiver part. So RC time constant of the diode and the associated circuit. So these are the three things which will dictate your response time. The transit time in the depletion region, I region, and the diffusion component which is there in the P and N region, and the associated circuit and the RC time constant of the photodiode. So now the question is how to choose your depletion region bit, because not everything is in your control. For example, alpha is not in your control. Then there will be some component, CJ junction capacitance, and associated circuitry will require some component. So, and then you have one component which is the length or the W, width of the depletion region, which is in your control, which you can reduce or increase. So let us understand what happens if I increase W to a high value or decrease W to a very low value. So there will be a trade-off. Let us try to understand. See, what I want that when my intrinsic region is wide, so there is a greater chance that the photon will get absorbed and electron-hole pairs will generate, which means my efficiency will improve if I make it wide. If I make it narrow, the chances are that photon may not get absorbed because it is quite narrow. The probability is low. So it may not result into electron-hole pairs, hence the efficiency will go down. So making it wide ensures that I have high quantum efficiency. But if I increase width, the transit time increases because this distance is increased. TTR increases. And when TTR increases, that F will get reduced if this increases. That means the bandwidth of the device gets reduced. So there is a trade-off between quantum efficiency and the bandwidth of the device. So accordingly, you have to, select the value of junction width, whether you want high quantum efficiency or you want high bandwidth. So generally, this is kept as, this value is generally kept as, let us see, so generally this is kept as W is 2 by alpha or 3 by alpha, where alpha is your in between in this range. That is ideal value to cap. So you get a good compromise between the quantum efficiency and bandwidth. So before we start the discussion on the Avalanche Photodiode, let me just give you an idea about the circuitry which is generally used in the photodiode. So you have, this is a photodiode. Light is falling onto it, and this is the positive part, this is the negative part, and then you have the current flowing here. So let me put a resistor here. This is say RL, and this RL is generally high. So before you give it to the next circuitry, you use some sort of transimpedance amplifier, which changes the high impedance, input high impedance to low impedance. So this is trans high impedance circuit. So what you get is sort of low impedance, and then you give this to some sort of amplifier and you collect it here. Say, let me write this as A. So if I draw a equivalent circuit of this, or AC equivalent circuit, it will be something like this. So this is the photodiode, and this is the current which got generated because of the power here. So let me call this current as IP, photocurrent, and this is CD, junction of the diode, CD, capacitance of the diode, CD, capacitance of the diode. This includes all the capacitance, and this is the amplifier part. Say this is amplifier, and this is the load part, and this is the amplifier resistor, and this is the CA part, and then this is the output here, V0. So this is the equivalent circuit, which includes this capacitance of the diode, the load, and the RC values of the amplifiers. And if I see the R effective, if I calculate, then this will be RL parallel RA, that is R effective. And if I see C effective, this is CD plus CA. And the total time constant will be R effective into C effective as a total time constant. So this will actually give distorted. So after this, if you want to correct this, which has the distortion has happened because of all these junction capacitances and the amplifier circuitry, then you have to use some sort of equalizer here, which will equalize the distortion which has occurred in the circuit. So at the output you get rather clean pulses, or the replica of the input. So this is how the whole receiver circuit will behave. Receiver circuit. Now let us go to another type of device, which is called as APD, Avalanche Photodiode. So Avalanche Photodiode, let me first draw the structure of Avalanche Photodiode. So it is again a structure where P is heavily doped, N is heavily doped, and then you have the I region as well here. So there is a I region here, And this device is actually, this is reverse biased, but heavily reverse biased with a very, very high value. So I'm making more cells here, which actually indicates that it is high reverse bias. So when electron hole pairs are generated here, then these electron hole pairs, because of this high reverse bias, they have extra energy and they enter into avalanche effect and generate additional electron hole pairs, which actually results into some multiplication gain. And that happens because of this high reverse bias. So there's an avalanche effect happening here. Which results into more number of electron hole pairs which are generated inside the I region. And if you see the responsivity of such diode, it gets actually multiplied by a factor m, which is mr. There is a responsivity if there was no avalanche effect. So this m is the gain which you get, and putting the value of r, the responsivity which you had calculated as efficiency into E by h nu multiplied by m. So that becomes the responsivity of the APD. There is a gain of m here. And this m is actually not constant. So it is it's a fluctuating value, right? So this m, because of this fluctuation, this m will keep changing around some middle value. So this, because of this process, random generation of more electron hole pairs, this will generate some sort of noise in the APD, additional noise. We have not discussed the noise of p and d, that we will discuss once we have discussed the APD part. So this will generate an additional noise other than the noise generated in a photodiode, which I will discuss subsequently, is called as excess noise. So on one hand, it gives you a gain, but at the same time, this diode also generates an excess noise. And it requires high reverse bias. So you require reverse bias. Earlier in PIN diode, maybe the requirement is about 5 volts for the PIN. Whereas for APD, it is greater than 20 volts if you want a good gain. So the high reverse bias is required, and it also generates some excess noise. But the flip side is that it gives you a gain of M. So now we will try to see the another about the bandwidth. Let us try to understand how much bandwidth is needed for different signals. So we have been discussing about the bandwidth of the source, bandwidth of the photodiode, but let us understand, suppose I am transmitting an RZ signal or a RZ signal, and RZ is non-return to zero. And RZ is return to zero. So suppose you have 1, 0, 1, 1. If I make an RZ signal, so this is my 1, and then this is 0, and this is 1, and this is another 1. Right? So this is corresponding to 1, this is 0, this is 1, 1. So this is an RZ signal. The RZ signal will be, in 1 it will for half of the time it is 1 and then it will come to 0. So this 1 will behave like this. So this is RZ signal, and 0 will be like this, and then again for half of the time it is 1 and then 0, and then so if this is T, this is here T, and this will be T by 2. So this is RZ signaling. The data which is coming can be in either NRZ form or RZ form. So what is the bandwidth the device required if you are having NRZ data or RZ data? So let us define R as the bit rate, and so R will be equal to 1 by T. So if I see here in a for example, I plot 1 0 1 0 to make it a little simpler. So this will be, this is 1, this is 0, this is 1, this is 0. So if I see the principal component, the sinusoid component here is this. I mean, if you sort of Fourier analyze, there will be different frequency component, but the principal component will be something like this. This is in case of NRZ. And in case of RZ, if I see here the principal component, first let us draw the RZ, will be if the frequency here is F, and the principal component, if I draw the RZ, which it will have basically F by 2, right? So this is giving you, say, total F frequency, the principal component in an RZ signal, whereas if you have RZ kind of signaling, the principal component will be F by 2. So for NRZ, I require, equivalent to this distance. Let me first explain you this. So the delta F, the bandwidth required for NRZ, will be actually R by 2 half. Here, I'm sorry, this is not F by 2, this is 2F, sorry. This is 2, let me redraw this. So if I draw this, so this bill becomes RZ. Let me see, for example, suppose I have all ones, or that kind of thing, all ones, for example. And if I draw the RZ return to 0 signal, then this will be, this is 1, this is 1, so this will be so on and so forth. And the principal component, if you see, of the sinusoidal in this is, we'll have a frequency 2F. So if I am transmitting a RZ signal, I require high bandwidth. And if I am transmitting an NRZ signal, I require smaller bandwidth as compared to RZ. So normally for RZ, why do you need RZ? Why you want to use high bandwidth? Because when you have raw data, and suppose it has a continuous runs of ones or continuous run of zeros, because at the receiver you have to extract timing from the signal. So extracting timing where you have very less number of transitions, in extreme case of long sequence of ones or long sequence of zeros, it will be very difficult to extract the timing. So you convert this into a signal which is rich in timing. So that is why you use, the RZ kind of thing, so that you introduce, transitions, and then when you extract, you are able to extract the timing information or the clock from the signal. So that is the advantage of using, RZ over NRZ. And NRZ also has a benefit, but timing recovery will be a little tough here, but it will require less bandwidth. So the delta F which is required for NRZ is R by 2, half. And delta F for RZ is R. Alternately, we can also understand this using, suppose I have a pulse like this. It passes through a circuitry which is in my case receiver, which is equivalent to a RC circuit. It will degrade the rising time and the fall time of the pulse, so you will get something like this. So this degradation is actually measured by finding out the 10% point and the 90% point. And then between this, whatever you get is the degradation. So this is how you can find out the degradation. And if I try to find out for a typical circuitry, this is the equivalent circuit, for example, I want to find out the degradation. So the voltage VCT, this is V0, will be, this is VCT, and V0 is internal voltage. It will be VCT is equal to V0 into 1 minus e raised to minus t, the RC time constant. And this, if I find out this transit time, let me remove this definition of transit time, and let me draw here. So this is the equivalent circuit, RC equivalent circuit of the, say, receiver, and this is V0, this is VCT, this is C, this is R, and this is my T10% point and this is my T90% point. So this is called as the transit time, TTR, will be given by just finding out the 10%, the degradation in the rise time can be found out by RC, ln 10 minus L1 by 9, and then you do some simplification. So this is equivalent to 2.2 RC. And if you calculate the 3 dB bandwidth of this RC circuitry here, this will be delta F divided by 1 by 2 pi RC. And if you put these values of RC here, then what you get is TR is equal to 0.35 divided by DF. This is for the RZ signal. And this is 0.7. This will become double because the bandwidth requirement for RZ is R and the bandwidth requirement for NRZ is half. So this will be 0.7 by delta F for NRZ signal. So this is the transit time calculation for RZ and NRZ signal. So the bandwidth requirement, for example, if you are transmitting a 2.25 gigabits of signal, the bandwidth, and this is NRZ signal, the bandwidth of the receiver which I require is half of it, say 1.125 gigahertz, for example. And if this 2.25 gigabits is a RZ signal, the bandwidth of the device which I require is 2.25 gigahertz. Right? Now we will try to understand the noise in the detection process. So briefly we touched some noise in case of APD, which is the excess noise. So we will now try to understand the noise in the detection process. So in a photodiode, there are basically two types of noise. One is called as short noise. So suppose this is your photodiode and there is a continuous light, say constant light, falling onto this photodiode. It will generate some current. Now this conversion of photon to current or photon to electron hole pairs is a statistical process. It is not, constant number of electron hole pairs will be generated and constant current will be generated. So what you get is actually this current keeps changing, though it has a mean 0, but it is changing with time because this is a statistical process, this conversion of photon to electron hole pairs. So this is called as a short noise. So more is the power, more is the short noise. So this is the source of short noise, and this is mathematically written as short noise I square ns. This is short noise. The average value is given by 2E I delta F, where I is the average current and delta F is the bandwidth over which we are trying to measure this short noise or the bandwidth of the device. This is depends on the bandwidth of the device as well. So the expression for short noise is 2E I delta F. E is the electronic charge. And as you see, the short noise is proportional to the current. The short noise which is generated is proportional to the current, and this current is proportional to the power. So the short noise which is generated, this is very important, is proportional to the power, or the optical power falling onto the device. More the optical power falling onto the device, there will be more amount of short noise current. So this is the short noise current. Let us discuss what is the dark current. So if there is no light, this is a photodiode, even then, because of the thermal excitation, some amount of current is generated in the circuitry. So that is called as the dark current. So in the absence of any optical light falling onto the photodetector, because of the thermal excitation, some electron hole pairs are generated and then result into some sort of current, and that current is called as a dark current. The value may be small, but it has some finite value. So the total short noise, one is because of the signal, this is because of the signal, and the other is because of the dark current. The total short noise will be combination of, this is the current which is produced because of the thermal excitation in absence of light, I is in presence of light. So the total average I square ns is 2E into I plus ID. So these two currents are added into the bandwidth. So that is the total short noise current. Let us understand what typical values, or try to calculate what typical values the short current has. So if I work at 850 nanometers and I assume there is a dark current of 1 nanoampere and my power is 1 microwatt and responsivity is 0.65 amperes per watt. And so the I which is generated, that is the photocurrent which is generated, is responsivity into power, which is 0.65 microamperes. And if I plug these values into the short noise expression here, so mean square value of short noise current. So this is, let me write here, this is mean square short noise current. You have to put all these values in place, and what you get is 2.08 into 10 to the minus 17. Remember, this is mean square short noise. So if I take the RMS value of the short noise, that is the square root of this, I get 4.6 nanoamperes. So in this case, it is quite low, but it can be high in some applications or in some devices, depending upon the numbers or depending on the power level. The power level was very, very low, 1 microwatt. That is why you could see, short noise quite low, nanoamperes. If you increase the power level to some milliwatt, there'll be increase of short noise. The other source of noise is thermal noise. Thermal noise, that is in the resistor, because electron hole pairs in the resistor is always there and they are always moving, and because of the moment there is some current happening there, some current flowing there, and that is called as the thermal noise. This you must have also studied in some earlier classes. So the value of the thermal noise current, average value is average square thermal noise current is 4 kb. This is actually Boltzmann constant. So this is actually this 4 kb T delta F into RL. RL is the load. Kb is the Boltzmann constant. T is the temperature and delta F is the bandwidth. So let us now get some indicative value of thermal noise current. RL, suppose I keep 500 ohms. The bandwidth of the device is 100 megahertz, or I am trying to do measurements over 100 megahertz. And T is say 300 degree Kelvin. And if I plug in these values, I get 3.3 to 10 to the minus 15 ampere square. And if I take the RMS value, this is 5.75 to 10 to the minus 8 ampere, and accordingly we can convert them through microamperes or nanoamperes. So these are the noise which is there in the photodiode. So just to recap, initially there was short noise for the photodiode, which depends on the input power, and then thermal noise, which is because the source is from the load resistor, because the presence of the load resistor. This was for the PIN photodiode. And similarly, APD, we studied one additional noise, which was excess noise, which came because of that multiplication factor, which is not constant, which is again a statistical quantity. So that generates some noise, so which is an additional noise which is there in the ABD. Now let us try to calculate the total signal to noise ratio. We know about the signal power which is coming, and we have already studied now different noise which are generated in the photodiode. Now let us try to calculate signal to noise ratio. So signal to noise ratio, first we will do for the PIN diode. So I'm sorry about this mistake. This is actually Boltzmann's constant K to the B. So signal to noise ratio, this is the current part. I is equal to RP, responsivity into P, and I square is R square P, and this is the noise part. So this was the short noise component, short noise. And this is the thermal noise component. So short noise has both from the signal contribution and the dark current contribution. So if system is short noise dominated, it is possible that in some system there is more short noise, less thermal noise, or more thermal noise, less short noise. So accordingly you can classify the system, either the system would be a short noise limited or a thermal noise limited. If the link is very long, say 100 kilometers or say 50 kilometers, the power which you get is here very low because it is attenuated here. And the power here low is, that means the short noise component is low. But if you calculate thermal noise, that may be high. Thermal noise may be high. So such a system is generally referred as short noise or thermal noise limited system. On the contrary, if you have a link which are very close to each other, the power which is coming onto the receiver is high because the length is very less, the distance is very less, there will be less attenuation, there will be more power here. So in this case, the short noise component will be higher and thermal noise component may be lower as compared to short noise component. So this system would be short noise limited. So you can have either a short noise dominated system or a thermal noise dominated system. If you have a short noise dominated system, then the first component, this quantity will dominate as compared to the thermal noise component, and SNR can be approximated as responsivity square into P square divided by the short noise component. If on the other hand you have thermal noise dominated, then this expression will be, this RL will come up, and then this is also KB, Boltzmann constant. So this will be responsivity square P square RL for Boltzmann constant into temperature into the noise. So now let us understand the noise equivalent power of the photodiode. The noise equivalent power of the photodiode is actually when, suppose you are calculating SNR. It has some signal power and the noise power. If that signal power and noise power are same, I mean that is the quantum limit. I mean if the noise power is more than the signal power, I cannot detect my signal. I mean the best is my signal power and noise power, they are same. There may be a possibility of recovering the signal. So the power which is required, or the power which is required where SNR is equal to 1 is referred as a noise equivalent power, or NEP. So we will try to calculate this NEP. What is that limit, or what, I mean one can call this as a quantum limit. So what is that power which will define this SNR is equal to 1. So in this case, because the signal is very, very low, that means the current which is generated I is much less than the current which is there ID. So in the expression of SNR, we will use this this inequality, that is I is much less than ID. We approximate, wherever it is I plus ID, we will assume that is ID only, because I is much less than the ID, because we are trying to calculate noise equivalent power, and putting this SNR is equal to 1. If you do these two things, then you get an expression for noise equivalent power, which is given by this. NEP is given by this. Then the units here are watts per square hertz. So NEP is 1 by R. Here R is this responsivity. It should be curly R. 2E ID. This is again Boltzmann constant KB into temperature divided by RL square root. So you get the units of NEP are watts per square hertz.